Good afternoon, everybody. Tonight we're going to talk about graph theory. Actually, we're going to finish up all the topics on graph theory in our handout, and we're going to go do a little bit of review of big O and binary relations because Andy just told me that there was some trouble on homework with some of the things, so I'm going to go back over a few of the topics that seem to be hardest for you. So first we're going to start with graph theory. And what are the parts of a graph? Just to remind you, we have dots and lines, right? What are the dots called? Vertices or nodes. And we have edges. So we have nodes and edges. Okay, so sometimes we have graphs that have nodes and edges, but they have one more thing. So here's an example graph. Say that these are cities that are connected by interstates. What is something else that you might want to know about these cities and the interstates that isn't really marked on here, besides the names of the cities?
Distance between them.
Right, distances. So we can actually label the edges with weights or distances or any other number that we might want, like prices. So numbers we can assign to the edges will be called weights. So I'm going to pick some random ones here. They're not so random because they're actually in the packet on page 14 if you want to look. And you don't feel like drawing this again. So this is called a weighted graph because every edge is given a weight. And we can use these for lots of things. So we can use it for distances if this is representing connections between cities. We can use it for the cost of using a connection. So this might be ways that these things can be connected through to the internet, and they might be, you might have to go to this place and this place to be connected to see or whatever, and that might be costs of those connections. Or it might actually be, you could also use it for a time delay or whatever. You can use it for anything, but it's very, very useful because then you can make choices of optimal connections based on those weights. So sometimes you might want to connect all of these nodes by the smallest weight for every connection that you have. So one kind of graph that we have is called a tree. And a tree is a graph that has no cycles. Is this graph that we have, is that a tree? No, it's not a tree. So a tree would be the smallest connected graph that does connect all of the vertices but has no cycles. And we can just start deleting edges to make something a tree, but in this case, since we have weights, we might want to delete the largest ones in order to make a minimum tree, right, a minimum weighted tree. So if we do that, that's called a minimum spanning tree. So a spanning tree is a tree that spans all the vertices, and a minimum spanning tree is one that has minimum weight on all of the edges. So the total weight of the tree is going to be at a minimum. So let's figure out what the minimum spanning tree for this is. There's two ways to do it. And one way is in your notes, and there's another way. So how would you make a minimum spanning tree for this graph? Do what?
You can remove AF.
Yeah, we could start removing the largest one first, right? So we could remove this one. Then what? We still have some cycles in there, right? So we can take out FE next, and then why didn't you take out AB?
Because then it's not a connected graph.
Because then it wouldn't be connected. That's very good. So we couldn't take out AB. Can we take out CE? Yeah, we can take that out because still D and E are connected, but now we know we can't take these out. The only thing we have left is this triangle in the middle, so we're going to have to take out one of those. So if we take out BF, this should leave us a tree. So let's check it out. and make sure that we have a tree left. So the way you can do that is just by redrawing all the nodes and then drawing in the edges that you left. Then it's really easy to see if it's connected or not, because you shouldn't have any dots out by themselves. So here we have a minimum spanning tree. So if we want to know the total weight of the minimum spanning tree, we add up these numbers, which is 44, 53, 68. So 68 is the weight of the minimum spanning tree for this graph. So can we delete any more edges? No.
Well, we can, but we reverse it.
We can't, because then it would be disconnected. So how many edges does a tree have in it? Do all trees have, for the same vertices, have the same number of edges?
Yeah, we have one less than the number of points, right?
Yes, the number of edges is one less than the number of vertices. And why is that?
Because to connect all of them, we'd only need one less than that many edges.
Right, we need to have one less than every edge in order to connect them all.
One edge between every single word or pair of vertices.
Right. So we need to have one less than the number of vertices, otherwise it's not connected. So if I have any less than that, it won't be connected. You can think of that like if I wanted to think how many edges will it take, I would think of putting them all in a line and how many edges would it take to connect them that way. And then that's n minus 1. If I have n vertices, I need n minus 1 in between all the pairs, consecutive pairs. And that's the sort of simplest way to think of a tree. Okay, and this algorithm that we just used is not the normal algorithm. The normal one is to start with the smallest edge and add it instead of deleting the largest, but both of them will work. Right? Should work, because I should come out with the same number of edges and come out with the same weight. Okay, so it doesn't matter which way you do it. If you start with the smallest one first and make sure you add it, so what we would have done is drawn these dots and then added the BC edge, then the CF edge, then the CD edge, then DE, and then BA. So that's called Kruskals' algorithm if you do that. So Kruskals' algorithm will find a minimum spanning tree. So MST stands for minimum spanning tree. So in this graph, I'm guaranteed to be able to get from one node to another because it's connected. And this is a graph of minimum weight. So it might not be that the cheapest way to get from F to A is actually to go on this graph, but overall, this is the cheapest way to connect them all. Okay, because actually here we have 31 plus 5 is 36 plus 8 is 44, which is actually cheaper than taking that 47 edge that we took out. But if that one was any smaller, if it had been 42, then it would have been cheaper to use that edge than to go on this MST path. So this doesn't represent the shortest path between any two vertices. It just represents the smallest weight tree that spans all of them. Okay, there's some other things with graphs that we want to look at, and one is called an adjacency matrix. So in lots of places we've looked at matrices one way to represent a graph is with an adjacency matrix. So let's make a graph. And if I want to represent who's next to who, basically, I can make a matrix. without even doing this one, what can you say about what this matrix is going to look like?
It's reflexive.
Okay, someone mentioned that it's going to be reflexive. Is it going to be?
No.
It's going to be symmetric.
It's going to be symmetric because if A is next to B, then B is next to A. It's not reflexive because I don't have any loops. I would need to have a loop going from A to A or a loop going from B to B. I'd have to have all of them in order for this to be reflexive. How about irreflexive? Is it irreflexive? It is because I don't have any of those loops. So A is next to B. And is A next to C? No. It is next to D. It is not next to E. So I can fill these out based on, so I know this is symmetric, so actually I can go copy this row into this column. Because these are what's next to A. Now next to B I have A, C, D, and E, so everything is adjacent to B. Next to C I just have B. And next to D I have A, B, and E. And E, all I have left is to put a 0 there. So this is a symmetric and irreflexive relation represented by this graph. And it's not a directed graph, so if it doesn't have any arrows, we assume that the edge means that the relation goes both ways. So every graph can be thought of as a binary relation that's automatically symmetric. It's not necessarily automatically irreflexive because I could have loops. Why is this useful? Yes?
Because then you can easily put the graph in a two-dimensional array.
That's right. I could store this in a two-dimensional array in a program, and this has all the data about the graph that I need. Now, there's one thing that I didn't mention. What if I happen to have two connections between A and B? What should I do to my matrix? I should put a 2 in there to represent that I have two edges. So from A to B, I can actually put a 2 instead and a 2 right there, and then I know there are two of them. So that's the only thing I needed to do was make sure I just count up how many edges connect the two vertices that are adjacent. Okay, so this is one good way to store a matrix. So what's an alternative way to store a matrix? Store a graph. What's another way I could store a graph?
Coordinate location.
I guess we could do something like coordinate locations. I was thinking more in terms of, say, an array of the nodes, and then each one with a little linked list to all the neighbors. That's one way you could do it. Okay, so that might be useful for a different kind of program. So some programs might just want to know what's adjacent this way, and other ones, it might be better to make a linked list. Now, which ones, how do you know which one would be better? Depends on what you're going to use your program for, right? So what kind of program would a linked list be best?
One like airline flights where you might add cities later on. You want to go ahead and hard code the array.
That's right. It might be nice to have a linked list if I'm going to add cities. If my graph is really representing flights, connections between cities, if I want to add things, it's nice to have a linked list. Because then that way I don't have to actually go in 2 dimensions and add something. If I have a linked list with neighbors from each one, I just have to add to the city that I'm adding the flight. Another thing is if I don't have very many values in this matrix, like if there aren't that many edges, a linked list from each vertex might be the best way to go. Because then, say that this is like 1,000 by 1,000 and I only got 100 ones in there. If I only had 100 edges, I don't think I'd necessarily want to go by 1,000 by 1,000 matrix every time I wanted to find the neighbors. So you want to make choices when you create storage about what kind of storage you need based on how you're going to have to look through things. So when you have small things, it doesn't matter how you store it. except that linked lists are a little harder to code than arrays, right? So probably I do this, the first choice. But for larger things, you have to start thinking about, why do I need this data? And then you want to store it in a way that makes it easier to retrieve whenever you're going to do the most retrievals, right? Okay, good. So a linked list would also be useful if I need to get all of the neighbors for something, because that would be real quick to go through all of them. Okay, how many people have their handouts with them? Everybody, pretty much? Okay, I'll just put this one up here. All right, one next thing, which I don't want to talk too much about, but one concept in graph theory is called an isomorphism. And that's kind of an intimidating word, but I just want you to see these pictures right here. In your notes, it has a graph isomorphism is basically when you have a graph that's the same shape as another graph. So it's really the same graph except somebody rearranged the picture. So these top two, these are isomorphic. But you might have to make a mapping from some of the nodes to the other nodes. So in this case, if we take a look at these two, I can see that these two are isomorphic if I look at this little triangle, V5, V4, V3. They're the same in both pictures. And then if I think about taking these, picking up V1 and V2, and then stretching them down over the other triangle and making it bigger, then you can see that these two things are isomorphic. But without someone telling you that these two graphs are the same, you might not see it. So you might want, if you need to know that two graphs are the same, like someone's sending you a bunch of data, and you need to know whether you have the same data over and over again, you might check, two things and see if they're actually isomorphic. And the way to check is to see if the adjacency matrices are the same. If you interchange the rows in your matrix. Because you could have relabeled the vertices, right? So they might still be the same graph with relabeled vertices. So isomorphism means you have a graph of the same shape. Like all the nodes will have the same degrees and stuff, but I might have to relabel them. And these two graphs on the bottom are also isomorphic. So you can see that by seeing that actually a line was drawn from V1 all the way to V7. See if you go around this curve right here, around the outside, you can see that that's the same. And then these other two are these crossing edges. Now, the reason why this is significant is because sometimes you need to make graphs planar. Because if you don't have them planar, they're kind of hard to read. Like you might think that there's a node in there. And there's lots of neat theorems about planar graphs also. So this one happens to be planar, but you can't tell in this picture. But if you draw it again in a different way, you can tell that it is planar. I can fit it in a plane without crossing any of the edges. That's what a planar graph is. So I just wanted to do a little brief introduction of that. I'm not going to make you do any isomorphisms because they're a pain. Okay. But I wanted you to know that we can have that happen. So we can draw two graphs, and they might look absolutely different, but they might really be the same thing. Okay, are there any questions? Like, what did we say was an Euler circuit yesterday, the last class?
Well, it has to have the same beginning and end point. If it's a circuit. And
so a circuit is a path that has endpoints that are the same. Start and end is the same. And an Euler circuit is what? E is for?
easy, right?
E is for easy and?
Edges.
Edges. That's the main thing, is edges. So I have to have all the edges in the graph in my Euler circuit. So how do I tell if a graph has an Euler circuit or not?
All the vertices have an even number of edges from it?
That's right. If all the vertices have even degree or they have an even number of edges touching them, then we have the Euler circuit. So this is another thing, all even. all even degrees. So that starts with the E too. Euler edges even. And this is easy because we use Fleury's algorithm, which just starts adding edges randomly, right? So I could take any graph and make an Euler circuit as long as it has degree 2 everywhere. What about an Euler path?
So what is this odd degree?
So I have exactly 2 with odd degree, and I can't have any more or any less. Right? And when I do Fleury's algorithm, what kind of nodes do I have to start with? I have to start with the odd ones. So I have to start on an odd vertex. So for Euler circuits, it doesn't matter which vertex you start on, it should work. You just keep adding edges to your path until you have no more left. So let's do an example. Okay, here's one. Just to make it different than the rest of my graphs. I did. I thought I turned it back on. Okay, our power went out, so we had a little break there, but now we're going to get back to finding an Euler circuit in this graph. And I made it on purpose so all of the vertices have even degree. So if you guys want to double check it for me, I think everything has, except for this one. C and A. There we go. No problem. 1, 2, 3, 4, 5, 6. Good. Now we have a graph where all the vertices have even degree, and we can find an Euler circuit. So this is how you can make problems for you to practice. Just make a random one, and then start making an Euler circuit. So when I do this, I just pick a random vertex. I'm going to pick A to start with. I'm going to need to leave myself some room here to write my path. So let's just go from A to B, and we'll just go along until we maybe have, what's the only problem we might run into?
To a corner.
We might leave a stranded vertex somewhere. So that's the only thing we have to check for when we're adding edges here. So what we do when we add one is we pretend that actually it's not there anymore. And just make sure we don't leave anything stranded that is still connected. Or leave ourselves stranded is what really the problem is. Okay, so let's just go ahead and add back BA, then go from A to E, and then E to B. I'm just picking random ones here. There's nothing else. So if anybody wants to pick one, they can call one out. We can go from B to C. I have no other choices, so I can leave B by itself there because I delete that vertex as soon as it's not connected anymore. Okay, so I went from B to C. And then from C, I can choose anything. Let's go to D. From D, I have to go back to C. And then from C, let's go over to,
No, E.
we can't go over to A because then we're stranded, right?
Yes.
So it's good to see that that's a choice we can't make at that point. We don't want to go C to A because then we leave this little loop. So we need to go to E,
Back to C.
back to C, and then
to A.
all the way to A. So there's an example of finding an Euler circuit. And it works just the same as an Euler path, except for on an Euler path you have to start on the odd one, and you should end on the other odd one. So Hamilton circuits do what? So this uses all the edges. A Hamilton circuit uses
All the vertices.
all the vertices exactly once, except for the start and end one, which we will list twice. So in this graph, is there a Hamilton circuit? So we listed A a few times, we listed B a few times. So if it was a Hamilton circuit, I would need to list everything exactly once. So can I possibly make a Hamilton circuit for this graph? I see some shaking of heads. Why?
Internal cycle.
Because I have a little internal cycle with the degree 2 vertex, right? Because D has degree 2, so I need to add those two edges in. But that makes a cycle with C. And I can't make any subcycles in Hamilton circuit. So that was very good. So we'll just do a summary of graph theory, and then I'll do some review of some other topics that we have. So a graph, usually represented by G, is a set of nodes and edges that join them. And we have paths. We need to know what paths are, and cycles. We have Euler circuits, which use all edges in a graph, and all nodes have to have even degree. And if they do, there's always an Euler circuit. And the algorithm to find Euler circuit is called Fleury's algorithm. And that's basically a random add an edge, unless you can't, algorithm. We have Hamilton circuits. So we have Hamilton paths, Euler paths too. And in parentheses, I'm going to put two odds here for path. Okay, so it's the same, except I have to start and end on the two odds for the Euler path. So we have the Hamilton circuits and paths also, and they use all the vertices each exactly once, except for the start and end. Okay, and this is a slightly harder problem to solve, but I won't give you any that will be too hard to solve on any tests. So you will be able to tell whether there is one. So what's the algorithm to find, like the generic algorithm that works for everything to find Hamilton circuits? The general algorithm that works for all of them is, the only reason why it's a bad one is because it's exponential. It's the one that lists all possible cycles that use all the vertices and then checks to see if they're in the graph. So if you had no other way to find the solution, you could list all possible cycles and check to see if they're in the graph. And this is an NP hard problem because it's exponential. And we know, because we just finished doing counting, that this is a factorial problem, right? All the orderings of n vertices is n factorial orderings. So NP hard does not mean unsolvable, right? For small graphs, it's definitely solvable, because 4 factorial is 24. Checking 24 things is not that bad. And besides, if you only have 4 nodes, you can probably look at it and tell if it has one, right? Also, if you have a graph that's fully connected, you definitely have one, right? If a graph has all the possible edges, it's called a complete graph. You don't need to know that, but just in case you see complete graph, that's what it means, is a graph that has all of the possible edges. Okay, then we have trees. We talked about that. And a tree is a graph with no cycles. So if the number of nodes is n, then the number of edges is n minus 1 in a tree. So we also had, we might need to find minimum spanning trees, right? So a minimum spanning tree is a tree of minimum weight which connects all the nodes of G. So if I start with G and I want a minimum spanning tree, I just need n minus 1 edges that connect the n nodes, and they should be the minimum weight ones. And Kruskals' algorithm will find that, and this just adds the minimum weight edge. And it repeats that until it's added n minus 1 edges. Except you can't add anything to make a cycle, right? Okay, what if you have two edges that are the same weight? You can pick a random one, so it doesn't matter. You can just pick whichever one, and you'll still get the same minimum weight. It might be a different tree, so you might have different solutions, but you'll have the same total weight. You just pick a random one if you have two edges with the same weight. Okay, we have our matrix representations for graphs. So that was an adjacency matrix. And it was symmetric. And it's a good computer representation for a graph. By the way, how do I write down an edge? Like if I were to list all my nodes, it's easy to list the names of the nodes. But what about the edges? What do I normally do?
Two vertices that it joins?
I list the two vertices that the edge is connecting. So, and I usually put a comma in between them, so I make an ordered pair. So to represent an edge, I would put A comma B, just like in our binary relations. And if I'm going to list a graph, I would tell whether it's directed or not. So if it's not directed, then AB actually means it goes both ways. AB equals BA, and both of them are in there. And the last part of graph theory is Hasse diagrams, which we already did when we talked about binary relations. But we can do a little review right now. So a Hasse diagram represents what kind of binary relation? It was a partially ordered set.
Oh, yes.
Okay, so the last topic in graph theory is Hasse diagrams. And that goes with binary relations also, right? So what we do is we're just going to take a graph for a relation, which we already know how to make, and we're going to rearrange it so we don't have to have any arrows. It has no loops. And also transitive edges are removed. So no arrows. All edges going up. So we know which way the arrows go. No loops. And no transitive edges. When I say no transitive edges, what does that mean?
4 goes to 3 and 3 goes to 4. 1 does not go to 4.
If I have 1, 3, and 3, 4, then 1, 4 has to be in the relation, right? Because it's transitive, because it's a partially ordered set. But this one is not drawn in the Hasse diagram. So we don't draw it. And why do we make graphs like this?
Find mins and maxes.
We can find minimal and maximal elements, but it also makes it a lot easier to tell what the relationships are. Because we know that the loops are there, and we know that the transitive edges are there. We just don't need to draw them. So it's a lot less complicated, and that's why we draw them like that. So like, you remember the partially ordered set for the power set of 1, 2, 3, and the inclusion relation? That was the subset relation. If we had to draw the graph for that, it would be amazingly covered with lines, right? So the maximum point was the set containing 1, 2, 3. And then what goes on the next level below that? All the sets containing 2 elements. And then these were connected, right? Now on the next level goes
Elements by themselves.
the single sets. So the sets with singletons. And then I connect the ones that are subsets of each other. Sorry, these on the bottom are subsets of the top ones, but it doesn't go the other way. And what goes on the bottom level?
Empty set.
The empty set. So I'd have a lot more lines in here, and this is already a lot, right? I'd have a lot more lines in here if I had to draw the reflexive points, because reflexive means that every single one of these nodes is a subset of itself, and I would have to draw a little arrow and a loop on every single one of them. And then transitive means I'd have to actually draw a line from the empty set to all the other ones. So in this graph, you can really see it's useful to make a Hasse diagram instead of drawing the entire graph. Okay, so anytime you're given a relation, you can make a Hasse diagram out of it. You draw the graph, and then you reorient it so all the edges go up. You get rid of all the reflexive points, and you get rid of all the transitive edges. So if I gave you a matrix that represented a binary relation, can you all make a Hasse diagram? Sure. Good. Because guess what? I will. How about now? So a partially ordered set has what properties? So if you had trouble with anti-symmetric, remember, if you had to draw the diagram, in a Hasse diagram, if I have to draw everything going up, that means that nothing on the higher levels can relate back down to the lower levels. That's all the anti-symmetric means. So that if I have an arrow going one way, it can't go the other way in my graph. Okay, so that's what it means. If you look at a graph of a relation, arrows only go in one direction. I don't have to have arrows going between every pair, but they're only allowed to go one way. So if something's reflexive, let's say this is a 4 by 4, then it has to have ones down the diagonal. Right? Now I can put ones anywhere else I want to. I'm making one up, by the way, right now. Except I can't put them across from each other, and then I have to make sure it's transitive. So let's see. I'll draw a graph for this while I'm doing it. So I just put 1 to 2. 1 goes to 1. And 1 goes to 4. Let's make I just made it symmetric, which isn't allowed, right? Okay. There we go. Now let's make 2 go to 3. Let's not, because then 1 has to go to 3. Let's make 2 go to 4. And that's good because it's transitive so far, right?
So 2 is 0, 1, 0, 1.
0, 1, 0, 1. 2 goes to itself. 3 goes to itself. And I can also make 3 go to 4. And then it'll still be transitive. And let's leave 4 going nowhere. So the matrix is going to be 1, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, and 0, 0, 0, 1. So this is a partially ordered set because I made it that way. It's reflexive, it's antisymmetric, and it's transitive.
Excuse me, does it mean that the graph also include number 4 goes itself?
Yes, I forgot to draw that one. Okay, and so this one isn't that complicated, but it's still going to be easier to understand if I draw it as a Hasse diagram. So let's do that.
Isn't that a symmetric point there? From 3 to, is it 4? 3 to 4?
3 to 4? No, because I don't have 4 to 3.
Okay.
So it's okay. So since it doesn't go both ways, since nothing goes both ways, I'm antisymmetric. The only difference between antisymmetric and asymmetric, if you look at a graph, is asymmetric wouldn't be allowed to have any of these loops. Because asymmetric means that if I can go somewhere, I can't go the other way, but I can actually go both ways on this little loop. That's why you have to take those out for asymmetric. Okay, so which one goes on top here? Like, what's one that I can't ever leave from?
4.
4. So 4 goes up on top, and 3 goes to it, and 2 goes to it, and 1 goes to it. So those are candidates for the next level, right? But 1 and 2 can't go on the same level, right? Because 1 goes to 2. But 2 and 3 can, right? Because they don't relate to each other. You can't put things on the same level if they relate to each other. So since these don't, I can put them on this level. I have to put 1 on the lower level, and it goes to 2. It doesn't go to 3, right? Okay, so which ones, are we done?
Could you put 3 on the lower level?
I can put it on the lowest level, it just can't connect, it just doesn't connect to anything else. So that's an alternative. You can put 3 also on the bottom. Okay, which ones are maximal?
4.
4 is maximal. Anything else?
It is a maximum.
Right, 4 is a maximum because it's the only maximal point. Are there any minimal elements?
Yes.
1 and 3.
1 and 3 are minimal. Is there a minimum?
No.
No, because there's more than one minimal element. Good job. How about what are the upper bounds of 1?
4.
1, 2, and 4, right? That's everything I can get to from 1. And you're forgetting there's a little loop on 1, so I can get to 1 from 1. So upper bounds of 1 are 1, 2, and 4. So what are upper bounds of 3?
3 and 4.
3. That's a 3 there. So that's 3 and 4. So what are upper bounds for the set 1, 3?
1, 2, 3, 4. No.
Just
Just
4,
4.
right? Because that's the only overlap between the upper bounds of 1 and the upper bounds of 3.
Okay.
It's the intersection of those two sets.
Why is that the intersection?
Because
You said so.
upper bounds of any set of things is things that are upper bounds for everything in the set.
Okay.
That's why it's the intersection, because it has to be an upper bound for 1 and an upper bound for 3.
All right.
Okay, so since there's only one upper bound for 1 and 3, that actually has to be the least upper bound also, right? So if I look at a set of upper bounds, so what is the least upper bound for 1? It's 1, right? So the least upper bound is the minimum if you look at the Hasse diagram just of the upper bounds. So if I was looking at 1, 2, and 4, I would pick the minimum out of that to be the least upper bound. If there's no minimum, there is no least upper bound.
That's the lowest level, not necessarily the minimum value.
Right, the minimum number might not be the lowest thing, right?
Right.
So they're on different levels. It's the lowest thing that you want to go with, not the lowest number. Okay, and all the lower bound stuff is exactly the opposite. Yes?
Since 4 goes to itself, does 4 have an upper bound of itself?
4 is its own upper bound. That's right. Every point is its own upper bound, and anything that you can get to above it. But I can't go down because the arrows all go up, right? But I do go down when I look for lower bounds, right? But for upper bounds, I always go up. For lower bounds, I always go down. Or stay where I am, because those little loops let you stay there. Okay, that's it for graph theory. So it's not a very complicated subject at this level, but it's a really good class. I recommend that you take graph theory if you like this stuff and you like proofs, because you do lots of induction proofs and proofs of properties of graphs and things that can be done with them. And you would look at gray codes again and recursion. And a lot of the things we've done in this class you would do again in a graph theory class, or combinatorics is another topic that looks at lots of objects like graphs. Okay, what we're going to do now is we're going to go back to a couple of topics that were hard in Big O and binary relations. I just went back over the Hasse diagram stuff. I think that you guys were okay with it, but I just wanted to go through and review all the topics that were related to graph theory. So let's go back to Big O for a few minutes. What I wanted to do with Big O today is, I think that the hardest thing in that was doing induction proofs with inequalities. Because we know the definition of Big O, right? What is the definition of Big O? F is Big O of G if there exists a constant C so that f of x is less than or equal to cg of x for all x where x is greater than or equal to k. Right? So I also have to actually say there exists a k. Right? Doesn't matter where I put the there exists a k. As long as I have a c and a k that makes this inequality true, then f is in Big O of G. Okay, so sometimes we have to actually prove that inequalities are true. And that's the hardest thing to do in induction. So let's prove one. So let's prove that 5 log n is Big O of n. So in an induction proof, I have to start with a basis and assume and prove. So if I'm proving this, I have to prove an inequality. 5 log n is less than or equal to c times n, where n is greater or equal to k. So what's k going to be in my induction proof? It'll be the basis, right? And what about c? I can pick it to be anything I want as long as I pick it and stick with it through the whole proof. So what number would you pick to make it easy? I would pick 5, so I can divide it out, and then I have no more 5s in my proof. Right? That's what I would pick. So let's pick that. Okay, so let's say c equals 5, and then k would be what? When is log n less than or equal to n? As long as n is at least 1, right? Log of 1 is 0. I can pick n equals 1. But your instinct to pick 2 is fine, right? It's okay to pick a bigger number. Picking 2 is good because then you never divide by 0, right? So if you have any divisions, you do want to pick 2 to use for your algebra. All right, so we're going to do this proof by induction. We're going to prove that log n is less than or equal to n for all n, greater than or equal to 1. So our basis is going to be n equals 1, so we want to show that log 1 is less than or equal to 1. Well, this is 0, so that's true. So writing basis assumed proof is no different for inequality proofs than anything else. It's the part after this that's different. But it works a lot like the regular induction proofs that we've done with equalities before. So we want to start with one of the sides that's easy to transform from the proof statement into the assumed statement, because we want to use what we know from the assumed statement. In this case, logs are hard to transform, right, if I have an addition inside. So I want to start with the right-hand side. So I'm actually going to end up proving, I'm going to reverse these. Just so we're used to working with the side we're going to start with. Okay, so we'll say that n plus 1 from the inductions, from the assumed step, the induction step, we know that's greater or equal to log of n plus 1. That's this inequality adding 1 on both sides. So this is the left-hand side of what I want to prove. So now I just have to get this right-hand side to be what I want. So now I want, instead of this stuff over here, I want that to be greater or equal to log of n plus 1, because that's what I want on the right-hand side of my inequality. And intuitively, this should make sense, right? Because n plus 1 and n are about the same size. If you take the log, that's a number that's way smaller than n or n plus 1. And then adding 1 to it ought to be bigger than taking the log of one bigger number, right? So when you do these proofs, it should make sense. Whatever you're trying to prove, it should make sense that it's true. Okay, now let's see. We want log of n plus 1 to be bigger than log of n plus 1. This is, if you don't know what to do, then you can do an induction proof. Okay, so if it's something that you can't see, like what to do, you know, ahead of time, then you can do an induction proof. So let's do that. Basis.
I thought we were doing
Hmm?
I thought we were doing one of
That
them.
we're doing that.
You're doing
Yeah, we'll
one
do another induction proof.
inside.
So I want to prove this statement. So I can do another induction proof. I'll do it on another sheet.
You can set 1 equals log, whatever the log n the basis is. For example, if the base is 10, it's equal to log 10. Then it equals log n plus log 10. That equals log n times 10. Is that right? That will get a
I mean,
code.
probably I don't need to do an induction proof for this.
Okay.
I could raise both sides to the 2, right? 2 to the both sides. Let's try that. See what we get. On the right-hand side, I get n plus 1, right? On this side, I can separate this, right? 2 log n times 2 to the 1. That's the reason for that. That's not good.
I thought it was n times 2.
Yeah.
Did I do
Two.
something wrong?
2 log n.
2 times
2
1.
to the 1.
Plus
Sorry,
log
2 to the
log
1.
n.
That's good. Okay. Brain dead for a second there. 2 to the 1 times that. So there's a proof. I don't have to do an induction proof. Any way you want to do a proof works. So this is like a little sub-proof for the thing that I wanted to prove. So if you read it that way, it looks like a proof that your geometry teacher would like. Did you guys ever have math teachers that were like, don't start with what you want to prove? Okay, I say just read it backwards. Okay, so there's a proof. So if that's true, then what? So I have this first statement here and the second statement here. If I combine those, I get what? Using something like hypothetical syllogism, kind of, or transitivity. If I know n plus 1 is bigger than log n plus 1, and I know log of n plus 1 is greater or equal to log of the quantity n plus 1, then I know what?
N plus 1 is greater than log n plus 1.
N plus 1 is greater than or equal to log of the quantity n plus 1. That's why I wanted this thing in the first place. Was because that's what I was trying to prove, was that I didn't care whether whether n plus 1 was bigger than log of n plus 1. I didn't care about that. I just got it from the assumed statement. What I cared about was this first thing being bigger than the last thing. So all you have to do is go over and do a side proof of this thing, and then you're done with your proof. So what you're doing in an induction proof is consecutively reducing your problem into something easier to solve. Right? I wanted to prove log of n is less than or equal to n for all n. So a problem easier to solve is to prove it for one step, because I can't write it for every single thing. That's why I do a basis, assume, proof. So I do a basis, assume, prove, and then I get to a part where, oh, I need to know something else. And then I can do any other kind of proof, even if it takes another induction proof here to prove whatever this is, then I can do that. So this is the magic step in an induction proof that has an inequality. That magic step is just to say, what is it that I want next that will give me what I want to prove? So I need to use my assume statement first to get the left-hand side or the right-hand side, whichever you're working with, of your proof statement. And then you will get an inequality that you'd like to be true, and then you try to prove that. And I promise I won't give you any in this class that you won't be able to do this way. Sometimes there are ones that are so tight, like these two things are so close together that you can't actually just have this function actually be in between them. Because sometimes you have to like multiply by like some really weird number to get it to fit in between. I'm not going to give you any that hard. Okay?
There's something down. Push it a little bit. Thank you.
So those two lines gave us what we wanted to prove. So then we were done with the proof. So having our little side proof also on the paper at the same time. So the only other thing that you had problems with on Big O on the homework that Andy told me was what to do when you had a product of two things. And I hate to even say this because what you do when you have a product of two things is absolutely nothing. So if I have n times log of n and I ask you what's the big O of that, you say n log n. It's a product. I only do stuff with big O with what functions? Plus. Sums are the only thing I do anything with, and I drop constants. There's no constants, no sums, I'm done. As soon as you get to the point where there aren't any sums and aren't any constants, you're done. You can even leave some constants, right? I can leave these kind of constants, like up in the power. Okay? And I could even leave, this would be an acceptable big O also, because n plus 1 is significantly bigger than n factorial, right? So I wouldn't necessarily drop that plus 1. So otherwise, I'm going to drop numbers and I'm going to drop any pluses that I have. So given that, let's figure out the big O of this function. So first I figure out for every sum, I figure out the big O of that sum, right? So for this first one, what's the largest term? N squared. I can even ignore the rest. If I want the constants, I can do what? Replace every term with, leave the coefficient and replace it with n squared. So it would be n squared plus 5n squared plus 3n squared. So that would be 9n squared, and then I would drop the 9, right? But quick and dirty is just to circle the big one. And why do I have to be careful about circling the biggest one? If I have a number of terms that depends on n, I definitely need to replace them all and count them all up. Because if I have 1 plus 2 plus ... plus n, the big O of that is n squared. Right? So I can't just circle the n. So if I have more than a finite number of points, so I have a finite number, but if I have not a fixed number, I need to count up the terms because there might be n of them. If the number of terms depends on n, you need to count them up. If it doesn't, you can just circle the biggest one. Okay, how about this one? E to the n. How about this one? Just n and cross out the 10. So what's the big O of this? N squared e to the n over n. I don't even care if you divide it out, but that's equal to n e to the n. So you have nothing left to do. After you're done with the sums and the constants, that's it. And if you have to do a proof, you just do what I said and replace everything with the largest. Any questions about that? So what is big omega? Big O is upper bound, and big omega is lower bound, right? So it's basically the same as big O, except your inequality goes the opposite direction, right? And what about big theta? So in big omega, all I have to remember is it goes greater than instead of less than. And big theta is big O intersect big omega. So F and G, if two things are in big theta, that means they're approximately the same size. Because if one can be both an upper and a lower bound for the other one, that means that I can multiply one of them by a constant and then by a smaller constant and sort of trap the other one in between. So that's what that means. Big theta means you have a graph like this. I can take G and F and multiply one of them by a constant to get a graph like this. So I have big squiggly one on both ends, and I have the other one in the middle. So I have C1F, C2F, and G can be in the middle. So I can bound G by constants times F. That means they have to be about the same size, right? So they can't be growing at different rates because eventually something would cross. So it's good to have a good understanding of those. So when you take the class, the next class, you'll be able to do this stuff. Does anybody have any questions? Okay, so the only other thing I wanted to review today was a few things from binary relations. So here's a binary relation. X relates to y if x is less than y plus 1. Let's figure out what properties it has. Is it reflexive? Before you even answer it, we can write down the definition of reflexive and plug in this definition into it. So the definition of reflexive is what? For all x, x relates to x, right? Or xx is in the set R. So if I replace xrx, what I have to do is replace the y in this definition. I have to replace that with x. So then x is less than x plus 1. Does that work? Yes? Yeah, if I add 1 to something, it's always bigger. So it is reflexive. How about irreflexive? Usually if something's reflexive, it's not irreflexive, but just so we have the practice, let's plug in the definition. So this says that x is less than x plus 1 has to be false for all the x's. In other words, that x is bigger than or equal to x plus 1 all the time. Doesn't work, right? So it's not irreflexive. How about symmetric? It doesn't look like it should be, does it? So the definition of symmetric says, if x relates to y, then y relates to x. So let's use our definition of this relation in this definition. So if x is less than y plus 1, that implies that y is less than x plus 1. It's not going to work, right? And if I'm not sure, I could try to get the y on the left-hand side of this one, right? I could say minus y less than minus x plus 1, and then multiply by negative 1 on both sides. Y is greater than x minus 1. So I actually can't get y is less than x plus 1 because y is greater than x minus 1. So they might sometimes be true, but in general it's not going to be true. All right, so let's pick an x and a y. So 2 is less than 5 plus 1, right? But 5 is not less than 2 plus 1. So this is not symmetric. Now, anti-symmetric, it might be, right? We'll have to check. So anti-symmetric, there were a couple ways to write the definition. For all x and y, if x relates to y and y relates to x, then x has to be equal to y. That's the only time I can have both of those. So replacing our definition of R, that means that x has to be less than y plus 1 and y has to be less than x plus 1. If both of those are true, the only time that can happen if x and y are equal to each other. So we have to see if that's always true or not. So we know x is less than y plus 1, and y is less than x plus 1. So let's plug this one into that one. We get x is less than x plus 1, which is x plus 2. So what we have to do is find out, are there any x's and y's that can fit in here that aren't equal? Okay, so here, if I solve for if both of those are true, I have x minus 1 is less than y, which is less than x plus 1. And let's suppose that this is on the integers. Are x and y equal? Yes, they are equal. Right? Because the only integer between x minus 1 and x plus 1 is x. Right? There's only one of them in between, one less than x and one more than x, and that's x itself, so y equals x. So that's what happens every time we have both of those being true, so therefore this is antisymmetric. It doesn't have to be the case that these would have had to been true at the same time, right? Because if this is always false, then this implication is true. Right? If this can never happen, then the implication is still true. So let's just say this didn't even have a plus 1 in there. If x is less than y and y is less than x, that never happens, right? So less than is antisymmetric, even though this never happens. In this case, this one does happen, but it only happens if x equals y. And then that's okay, because that's what antisymmetric says. The only time this is allowed to happen, where both, if you can reverse the order and still be in there, then x equals y. So we just have two properties left, which is asymmetric and transitive. And I'm going to do them kind of quick since we just have a minute. So asymmetric says, for all x and y, if x relates to y, then y cannot relate to x. But I just said that sometimes x equals y, and I can actually have x relates to y and y relates to x sometimes, so this is false. But I also know it's false because asymmetric is also irreflexive, right? And this was not an irreflexive relationship, it was actually reflexive. The last one is transitive. So here I have to check. If x relates to y and y relates to z, does x relate to z? So in this case, I have x is less than y plus 1 and y is less than z plus 1. Does that imply that x is less than, just less than, z plus 1? So we can check that. So if I plug this one in, I get x is less than z plus 1 plus 1, which is equal to z plus 2. And so x is less than z plus 2. It's possible it could be equal to z plus 1, right? So let's just see. If we have 2 is less than 2 plus 1, and 2 is less than 1 plus 1, because yz would work, right? If z is equal to 1, that's not less than. Has to be less than, so I can only start with 2. So that actually makes, that actually works. So I would actually have to do a little bit more work because there's a gap in between these two, but I'll let you go and finish that at home. So you would just have to keep checking that to make sure that it was transitive all the time. So I'll see you next time.